Okay, so this problem is 32, chapter 11, Giancoli 6th edition. So this is a problem with pendulum. So they give us the length of this pendulum. They give us the mass of the bob, the pendulum bob, and they also give us the angle, the initial angle, the vertical, the angle with respect to the vertical that this pendulum bob is released. Okay, and then comes the questions. First question is the frequency. Okay, so what is the frequency that this bob will vibrate? Assuming that this is simple harmonic motion. So assuming that it's simple harmonic motion means that we didn't displace this pendulum too much, so that the sine of theta is approximately theta. And that means that we can have a restoring force that is related to the simple harmonic motion. Okay, so all that to say that the force, the restoring force, is approximately minus mg theta, okay, when we have a simple harmonic motion. Okay, remember that what we said in class, when we are playing with the pendulum, the force is written like this in terms of the angle, or we can also think of it like this. This is the angle, and this is the arc x, and this is the length of the pendulum. So I can also write this equation as minus mg. Remember the definition of radians, right? We have the theta is the arc divided by the radius. So I can write this as xl. So this whole thing here, minus mg divided by l, plays the same role of k, of the spring constant, when we are playing with the spring. Okay, so all the equations that we found for the spring can also be used for the pendulum also. The only thing that is that instead of k, we are going to use mg over l. Okay, so we have found an equation for the period for the spring, which was the period is equal to 2 pi square root of m over k. All right, so now we are going to use 2 pi square root of m. Instead of k, we are going to use mg over l. So that means that the period is now 2 pi square root of l over g, and period is 1 over frequency. So we can use this equation here to find the frequency. We have L, we have G, so we have the frequency. The next question is a little bit more involved. What they are asking is, what is the speed of the bob when it passed through the lowest point? Okay, so what is the speed of the bob when it's here? Knowing that it started here. Okay, so initially it had that angle of theta 0 that is given to us. Okay, and we want to know what is the speed down there. We know that this will be the maximum speed. Okay, so how are we going to find that? We can use conservation of energy just as we use to the spring. But what we need to remember now is that we don't have elastic potential energy, but we have gravitational potential energy. Okay, so we start at this point with maximum gravitational potential energy, which is mg multiplied by this height here, by this height. Okay, and down here I will have now maximum kinetic energy, which is 1/2 of mv max squared. Okay, so now I have to put these two equations together to try to find this Vmax. But what is remaining to know here is what is this height. So how can I find this height? Let's see. This whole length here is the length of the pendulum. What I need to find is this piece here, because then I will be able to see this whole thing. I know it's L. It's just the length of the pendulum. So if I find this little piece here, let me put this little piece in blue. If I find this little piece here, I know what the height is. The height is the total length minus that little piece in blue. So what is that little piece in blue? Well, you see that here in blue, we have a right triangle. don't we? Where I have the angle theta, theta 0, and I have the hypotenuse L. So this means that this little piece here in blue is L cosine of theta 0. Okay, so this is this piece here. Can you see that? I have the angle. This side here that I was after is the adjacent to the angle. So that's why it is L cosine of theta. Okay, so the height is the whole length here minus L cosine of theta 0. So this is what we need to know. And now we can find the maximum speed, the speed at the lowest point by using conservation of energy. So we have 1/2 of mv max squared, that's what we are after, the v max here, equals to mg L minus L cosine of theta 0. So you see the mass is cancelled, it doesn't matter if we don't know it, and now we have all the information to find V max. Okay? And the last question, now it's not going to be hard. The last question is, what is the total energy? Well, what is the total energy? I can use 1/2 of m V max squared. I just found V max, or if you prefer, you can use the potential energy, the gravitational potential energy, mgh, and we found h already. So that's the end of the problem.